Okay, let's go on with signal block diagrams. Yeah, we are in the chapter SBDs. Chapter 2.1 explains the three basic elements, and now in chapter 2.2 we want to talk about and learn how to set up a signal block diagram. What I have told you is that the signal block diagram is a graphical display of dynamical behavior. More in detail, we can say that we need equations. So we can say a signal block diagram is nothing else than a representation of an equation system. Yeah, so we need first an equation system containing physical laws, and this then can be converted into a signal block diagram. So a signal block diagram is nothing else than the representation of physical equation systems. Let's start with a very trivial, simple example, and then we want to make it more and more complex so that you can follow and understand what we want to do now in chapter 2.2. Let's start with a resistor, electrical resistor. The symbol of a resistor is just here, this box, and we assume that there is a current through a resistor, and if there is a current, we have a voltage over this resistor. The physical law of the resistor is the Ohm's law, and you can say the voltage is the product of resistance times current. This could be a DC or an AC signal, so U is nothing else now than a dynamical function of the voltage, and I is a dynamical function of the current. So in a signal block diagram, we have learned there are boxes, and boxes have outputs and inputs. There is a cause and response. The question is, what is a cause in a resistor and what is a response? Answer is, this depends on the application. If I have a voltage source connected to my resistor, then the voltage is the cause, and at the following response there will flow a current. In another application, there could be a current source which forces a current through a resistor, and then the voltage drop is a response. So depending on the application, only the application defines what is input and output. So a simple resistor has two possible signal block diagrams. First version, it's also a box, not so small like the symbol of the resistor, and we have arrows, input arrow, output arrow, and we can say, okay, first application is voltage source connected to a resistor, so the voltage is the current, is the input, and the response is a current flowing through the resistor. And now, very important, the block function mostly is described with the transfer function, and the transfer function of a system is nothing else than output as a frequency function, output signal, the function of the complex frequency p, divided by input of the frequency p. So we can say, another writing, the output is transfer function times input. Yeah. So in our case, if I is the output, then we can convert the Ohm's law in the way that we can say I, of course, is U divided by resistance. Then we can say, okay, the transfer function, if U is the output and I is the input, the transfer, if I is the output and U is the input, we can convert it, I divided by U is 1 over r. The transfer function in this case is the inverse of the resistance to admittance. Yeah. In a second version, so this is the first version of a signal block diagram of a resistance, then we have also a second version. You can say, okay, now I connect a current source to the resistor, I force a current through the resistor, and as a response we can measure a voltage drop. So now if U is the output and I is the input, then the new transfer function, now this is 1, this is 2, the new transfer function is U over I is the resistance. So we can say, okay, in our case the resistance now is a function if I is the input and U is the output. We can say, read U, the voltage, is function R times I, Ohm's law, or I times function, I is equal the function times input, so I is 1 over R times U, Ohm's law in this reading. Yeah. Okay, that's the first thing what you have to learn. One system can have more than one correct signal block diagrams, depending on the application. Now a step further. Let's assume not a resistor, but the next element, a component we can discuss, is a capacitor with a capacitance C and with, again, a current through the capacitor, could be an AC or DC current, and a voltage over the resistor U. In time domain, you have learned something about a capacitor. The capacitance equation in time is the following. Note what I want to mention in the using of lower and uppercase letters. The normal way to do this is I of t, U of t are time dependent physical dynamical values, and if I convert these values into the frequency domain, maybe you have seen this symbol, this conversion symbol, then we use, it's common to use uppercase letters. Lowercase letters for time values and uppercase, sorry, das ist natürlich Quatsch, and uppercase letters for the frequency variables. Yeah, and this symbol is the connection via Laplace transformation. Yeah, and time function U with lowercase u can be converted via Laplace transformation in a frequency function with uppercase U. Yeah, this normally appears in the following situation with the capacitor. The following way you have learned the current through a resistor is dependent of the change of the voltage. If there is a voltage change, then we have a current, and the proportional factor of the first derivative of the voltage is the capacitance C. So the physical law of a capacitor is I is C times du over dt. That's the time domain equation, and in the same way we can write down the frequency domain equation. We know something about the Laplace transformation. The first is, I have done this before, the frequency function is written in an uppercase I of a function of the complex frequency p, and if there is a multiplication with a constant factor, then in the frequency domain we have also a multiplication with a constant factor. If we have the first derivative of a signal, then in frequency domain this is equal to the multiplication with a complex frequency p. So in frequency domain, the same equation can be written with the complex current is C times P times complex voltage. So we can now again convert into signal block diagram picture. Again, either the voltage U or the current I could be the cause, and the response is then the U or the I, the opposite. So if the current I is the input and the voltage U is the output, then we need the transfer function FFP, which is output divided by input. And if we replace this, output U divided by I is 1 over P times C. So the transfer function of the capacitor is then 1 over PC, the complex impedance of a capacitor. Second version is if I have now the opposite application, if I have a voltage through over a capacitor and I want to have the current as the output, then I can write the signal block diagram in this way. U is input, I is output, and I is P times C times U. I is P times C times U. So depending on the application, you have two different possibilities to replace a capacitor with a signal block diagram element. In the workbook, see more elements in workbook page, let's wait, page 5 for the same method used for an inductivity, and page 6 for mechanical elements. Let's have a quick look into the workbook, page 5 and page 6, and then I can show you what we can do with any other elements. Yeah, on page 5 you can see this is what I have told you about the resistor. These are the Laplace transfunction elements, capacitance, Laplace transfunction elements. I have told you here are the physical equations in time domain. Here as addition, the same situation if we have the Phasor domain. So in German komplexe Wechselstromrechnung, where the differentiation is replaced by a multiplication with j omega and the integration is replaced by 1 over j omega. Yeah, the both columns here and here are very the same. If you replace the P with j omega, you get this. If you replace the j omega with P, you get this. So if you have Phasor domain, so this is true for sinusoidal signals, or you have Laplace domain, this is true for switched signals, you see the behavior is very similar. If we go in another area, the mechanical area, we can do the same. Here you see a damping element, or a spring element, or a mass element can also be converted into block symbols, signal block diagram symbols. The Newton's law, for example, gives this block behavior, the spring law gives this behavior, and the damping law, so the force is proportional to the velocity, to the speed of the movement, it gives this. The same can be done in rotational elements. Rotational elements have also damping elements, spring elements, and mass elements. Then the mass is called inertia. The rotation mass is inertia. And then the same rules can be applied. So you see independent what you have here as mechanical elements. This, if the physical laws are applied, these can be converted into signal block diagram elements. So any area with physical laws is able to express dynamical behavior with signal block diagram elements. Next step. Now we increase complexity by combining two elements and discuss what happened there. So the a good application is a voltage divider. Example, voltage divider. There we want to use a resistance together with a capacitance in the following application. A circuit where we have an input voltage possibility, so this is U1, then we have a resistance R, a capacitance C, and an output voltage U2. And we want to have now the signal block diagram of this circuit. First, what we have to do, if we draw a signal block diagram, we have to define input and output physical value. And in our drawing a signal block diagram, we would like to have the input on the left side showing to the right side, and the output U2 on the right side also showing to the right side. So this is the frame of my signal block diagram, and the task is now to connect U2 with U1 with the correct signal block diagram elements, and this is possible if we have an equation system of this circuit. So first we look at the circuit, we put down equations, and then we convert the equations into a signal block diagram. Okay, let's collect equations. If I have electrical circuits, then of course the Kirchhoff laws, the node rule and the loop rule are valid. That are the elements to write down physical laws. So I think it could be good that we first collect the equations. We assume that the output current, E output, should be 0. So this voltage divider is in the first step unloaded. So we have here in current, we assume if there is a voltage U1, there will be a current through this branch, and this caused a voltage drop over the capacitor. First rule is the loop rule, Kirchhoff's law for voltages. The voltage sum in a loop must be 0, so we can write U1 is, I think you have learned it in other lectures, U1 is the voltage drop over the resistance. This is with Ohm's law, I times R, plus U2. That's the first, we can say mesh rule or loop rule. So in green. And the second rule is, of course, I have used already the voltage drop over the resistor, so the Ohm's law is already used. I know the current now, I, has to be flow through the capacitor because this current is 0. So the node rule at this point forces this current flowing through this capacitance. And here the current through capacitance and voltage over capacitance we have done here with the capacitance rule. So we can say U2 is 1 over PC times I, or I is U2 times PC. So first step is done, the physical laws are set up, and now I want to connect U2 with U1 with these equations using signal block diagram elements. And the strategy is very simple. To fill this, now we have to go back from the output looking for equations to the input. So the first thing is what we have to look for is an equation which gives the output U2. U2 is anything. And you see here this equation is already available, prepared. So at once we can draw this equation as a signal block diagram. So we can say U2, what is this? U2 is I as an input multiplied with 1 over PC. The multiplication with 1 over PC is my block function. 1 divided by PC. And I know this is the input value I. So that's the first step. We see the first equation here. What we have used is this equation, and what we should do is we should mark this equation with a check mark or anything else. So we should never use one equation 2 times. That is a very fundamental law in an equation system. You also should not use an equation 2 times, otherwise your equation system cannot be solved. Yeah, so each equation should only be used 1 time to draw a signal block diagram. And now we have a new gap. This new gap has to connect the current I as an output. Here's an input. So I use now an element which has I as a current output. So I use an equation which is written as I is anything else. So what I have to do is now look for an equation which contains I. We have only 2 equations, and this equation contains I. And I have to solve this equation to I, in respect to I, because here I need I as an input. And if I draw the signal block diagram in that way that I is an output, then I can connect this output I to this input I. So what I have to do is I solve this equation in respect to I. So this gives I is U1 minus U2, U2 on the left side, is 1 divided by R multiplied with U1 minus U2. This is the first step. Depending on my drawing here, I need here I as an input, so I need an element which produces a current I. This is can be done with this equation, and the drawing of this gives if I draw this, we have an I output multiplied with 1 over R. This is a block function, 1 over R. And the input of this block is U1 minus U2. Is U1 minus U2. And this element now can be shifted in that position, so I can copy this. Yeah, what I do is I use this element to fill this gap. I is the output, so this fits to this input. The function is 1 over R, and yeah, here the input is not U1, it's U1 minus U2. How can I get U1 minus U2? Go back to the elements. The difference of 2 voltages is easily drawn with a summing point. So I can here just use the summing point. And the summing point needs U2 with a negative sign. Where can I get U2? Okay, with a junction point. If U2 is as an output available, I just connect with a junction point a branch, and then I have the signal U2 at my summing point. So just connect this, make a junction point. Ready is the signal block diagram of my RC low pass filter. Yeah, and for example, I can put this into MATLAB Simulink or in other simulation programs and then I can calculate step response or Bode plot of my RC circuit. That is the first version. I should mention, first version, and I will show you that in the same manner you can use the same equations, the same circuit, and get a totally different second version signal block diagram, which is also correct. Second version. The second version starts with the same strategy. Input must be U1. There is no other application possible. Normally, of course, you can also say this is input and then this is output, but this is senseless, because if this is a voltage, this voltage source, then this voltage source is just connected directly with C, and if this is an ideal voltage source, this has no effect, and then you have just a resistance here without, if this is unloaded, no current, so then the use of this circuit, if this is the source and this is the response, is senseless. It's nonsense. So we can only say this is input, this is output. Again, we do this the same way as compared with the first version. The difference is now, I look now for an equation. I start, the strategy is again the same. I start with the output signal and looking for equations going back up to that I have connected to the input signal. And the second version is just looking for the first equation, because the first equation also contains U2, and I can solve the first equation in respect to U2 in the way that I say, okay, I subtract on both sides I times R. What this is, the drawing is the following. U2 is the difference between two voltages. Difference means I have a summing point where the one input is my U1 and the second input is negative the voltage I times R. So this is a drawing of this equation. Now I need I times R as an input, so I need now the second equation, and I have only the second equation, where I times R as the output. This cannot be done. We have learned that branches should only contain pure physical values, but it is very simple to draw this in the manner that if I have just a multiplication with R, if I multiply the input current I with the resistance R, I get the voltage I times R. Ohm's law, we have done this before. So I have now the open input I, so I need now a second equation. You see, same equations, but now solved to the current I is P times C times U2. That means output I, this block, this equation can be drawn in that way. I is the output, U2 is the input, and U2, the input signal, must be multiplied with P times C to get the output signal. So this element now I use to shift to this position. I output can be connected to I input here. So I have very simple a block function. You can also draw this with an output in the top line and the input in the bottom line. That is no problem. The function is PC and the input here is U2. And again, to get the U2 signal here as the input, I need U2 as an output. This is available at the summing point. So now I connect the output signal to the input signal, and you see now if you compare both signal block diagrams here are totally different, but they show the same physical circuit. So one physical application can be drawn in two versions as a signal block diagram. You see here and here. Both signal block diagrams are correct. Both signal block diagrams are valid. Both signal block diagrams can be used. If we simulate them, if we try to simulate them in a digital simulation system, there is one thing where we can say one is better than the other. We can say here, this P times C, the multiplication with P, comes from a differentiation. The inversion of PC, 1 over PC, has something to do with integration. The opposite of differentiation is integration. So this is an integrator. And in a digital simulation system, integration is much easier to simulate and as a differentiator. So in a simulation system, I prefer the first version. But if you don't want to simulate it with a simulation system, both signal block diagrams are identical and can be used. Okay, let's do in the next video some more examples, learning setting up signal block diagrams.